Hi, I'm Zaynah Dargaye, engineering manager at Nomadic Labs, working on Tezos L1 related projects. Today I'm joined by Diane Gallois-Wong, one of the brightest minds working on the reduction of block times that we bring to Tezos. Our ultimate goal is to offer to users a fast and seamless transaction experience similar to electronic payments while maintaining accessible decentralization. That means ensuring the validators can participate without high requirements. It enables broad participation, so we have a secure and resilient blockchain while ensuring a censorship resistance, keeping Tezos open and permissionless for everyone.
And what were the key milestones along the road to 8-second block times?
The road was not that simple and was incremental along several protocol versions. We started with a block time at 60 seconds to come to 30, then 15, 10, and finally 8 on mainnet with Quebec. So the first part was about avoiding heavy computations that happen on the wall networks. What we did was to avoid applying the full block and operations in place where it was not required, introducing a new lighter validation, mostly doing checks. In Nairobi, the block time was reduced to 15 seconds. In Paris and Quebec, we identified that in some place inside computations around these validations, there was still computations that depends on the invariance due to full applications. So what we did is to put in place strong validations and identifications of bottlenecks. So we identify them, analyze them, try to find out how to optimize them while respecting all the invariants of the protocol, and then fix them. We did that along two protocol versions, so which were Paris, where we reached 10-second block time, and then Quebec, where currently on mainnet we have 8-second block time. And we did all this road with in mind preserving the hardware requirements, which are low on Tezos. So that means that all our simulations were testing that they are still compatible, and also the incremental way we did it along several protocol versions, what means to observe on the real networks how the old networks supported this reduction. So Jan, maybe you can explain what were the most challenging part in this kind of project.
I'd say it comes down to all the steps involved in enacting a consensus algorithm over a decentralized network. So you know that Tezos uses a Tenderbeck algorithm. It's a consensus algorithm that guarantees two-block deterministic finality and is resilient to 33% of Byzantine agents. But this Tenderbeck algorithm requires a lot of steps to happen in between each block. So first you have one validator is selected and has to craft the block. And then this crafted block has to be propagated over the network. When each validator receives the new block, it has to check it over to make sure that it's correct. Once it's sure that it's correct, it issues a first consensus vote operation that we call pre-attestation in Tezos. Then all these pre-attestations have to propagate over the network again. And once a validator receives enough of them, like when it meets a threshold that we call pre-quorum, it can finally issue another voting operation called attestation. And these attestations also have to propagate through the whole network. And then finally, the validator selected to craft the next block needs to receive all these attestations in order to be able to issue this next block. So this means that in order to have a healthy chain that moves on time, you need all these steps that I described to happen in between each block.
In the first place, you worked on a very important project actually that makes this computation more smooth over the networks. Can you explain a little bit this project and his challenges?
So we call this a pipelining project. So the idea is that you have several agents that are working, and the work of some of them depends on the others. The key point of optimizing all this is to make sure that you unlock the next agent as early as possible. In Tezos, the agents are the nodes of the network, and the work they have to do is, when they receive a block, everything that is needed in order for the chain to progress. And that includes a lot of things, but notably checking that the block is correct, and also updating the state of the chain. That is, for instance, if the block has a transaction where I send 10 Tez to you, then the state needs to be updated to lower my own balance by 10 Tez and increase yours by 10 Tez. In order to let the other nodes start their own work, you need to send the block to them. But to send the block to them, you need to check that it's correct, because you don't want to propagate bad blocks over the network. So first, we want to do all the checks that the block is correct, and then everything else can be done while the other nodes can start working on propagating the block too. Checking the block is critical, but it's also much faster because it's read-only, whereas writing into the state, like updating our Tez balances, takes a lot of time. But in order to make this possible, we had to really separate the validating part, checking the block is correct, from the application part, updating the balances. And so we had to redesign a lot of the Tezos code base.
As it's spent a lot of critical components in the code base. What are all those big challenges, example, you have in mind?
One example is that in every block you need to have something that tells exactly what the state is like for everyone, to make sure that everyone stays synchronized on the state. To guarantee this, each block contains something that is unique to this state. In technical terms, it's the hash of the state. Before the Lima protocol, the block contains the hash of the state after its own application. And that just doesn't work with pipelining, because checking this is absolutely critical. So it needs to be done during validation. But if it's the state after block application, you can't do it without doing the full application of the block. The solution to this was to change it so that it contains instead the hash of the state before application of the current block and not after. And we did this in the Lima protocol in 2022.
How taking into account constraints on hardware requirement affect your work?
It's a complicated constraint to take into account indeed. We have to assume that some validators run on the minimal requirements, and we have to take into account that they could have any role in the life cycle of a block.
Then what we did concretely to reach 10 and then 8 second block time currently?
So we did a lot of careful code analysis, experiments, tests, profiling, looking at all the different places in the lifetime of a block where we can gain some time.
So you say that all these changes implicated really critical operations for running a blockchain. Say, in terms of vulnerabilities, what methodology, what has been taken care of?
So we had a very rigorous approach, and for instance, we used conflict-free replicated data types in order to make sure that valid operations can be applied no matter in which order they are. And so we did a lot of model-based testing on it. And then once again, we did a lot of benchmarking, prototyping, and also we were very incremental in reducing block time. Each time giving us time to monitor how it actually behaves on mainnet.
On a personal level, what did you learn during this project?
It was actually my first big project in Nomadic Labs, and I learned a lot during it. It was about making big changes all over the code base. During it, I discovered the protocol and baker parts. I discovered new parts of the node, and it was really interesting to see how they all interact with each other, and how any change we do to one of them has to be taken into account in all other components. Can you tell us what's next for Tezos proposals in terms of further reducing block time?
On the Tezos X roadmaps, the goal is by the end of 2025, early 2026, is to reach 6-second block time on the layer 1. To do that, we have 2 tracks which are ongoing under refactions and works. First is to completely and fully use pipelining by making some parallelization in the mempool, which is a port on a node who validate operations that bakers will text to craft a block, and that's become feasible now that we are investigating into having OCaml5. The second track is about keep continuing to lighten heavy computations. This is doable by addressing signature checking. So we looking at aggregating attestations, say several into one only in a block. So we expect a much more reduction on application computation on that. And the last one is, as you know, layer 1 is becoming a settlement layer with consensus and economics model of test by staking and governance. So that means that the computation and execution of smart contracts will go to migrate into Tezlink. Tezlink is meant to be a smart rollup where the Michelson smart contract will be executed. So thanks to this 3 track, we hope to reach 5-second block time on Tezos. We continue to think about this block time rejections, and we did it incrementally. We will still do it incrementally by keeping this accessible decentralization and making sure it's safe for the network to go to support this rejection. Thank you very much, Diane, and stay tuned for more.